This problem and all other practice problems for Calc 2 here at Rutgers can be found in Sarai Studies. A link is in the description box below. Does the following series converge or diverge? Because I see factorials, I'm going to use ratio test. And the rules for ratio test are based on the limit as n approaches infinity of the absolute value of your sequence, but wherever you see an n, you add a 1 divided by your sequence. And that's equal to a limit, or in Rutgers we say rho, even though it looks like a p, or it is a p, we pronounce it as rho. So if rho is less than 1, rho is greater than 1, rho is equal to 1, or does not exist, then the ratio test tells us that this series converges absolutely, diverges inconclusive, meaning try another test. So we're going to take the limit as n approaches infinity of our sequence, but wherever we see an n, we're going to add a 1, so it's 2n plus 1 divided by n plus 1 factorial. So this is this, and then we would divide by a of n, or we can multiply by the reciprocal of a of n, which is just you flipping the numerators and denominators, which is what I always do, n factorial 2 to the n. At this step, always switch your denominators, because now you'll get the things that are most similar next to each other. And it's easier to see what you can do, because this here becomes 2 to the n times 2 to the first, and then you can cancel these out, and then you're just left with 2 to the first, which is just 2. To simplify an expression with factorials, ask yourself, what is bigger, the numerator or the denominator? Well, in the numerator, I have n, in the denominator, I have n, but in the denominator, I have n plus 1. So the denominator is bigger, so I'm going to leave what's smallest alone, and I'm going to expand what's bigger, so that's this. So I start with what I have, n plus 1, and to get to the next thing to expand, you just do minus 1 each time, so 1 minus 1 is just n, and then I know to stop here, I'm going to add factorial, because here I see what's up here, and so I can cancel them out, and so I'm just left with 1 over n plus 1. And then here, you could just take this 2, put it right here, because you're multiplying. As for the absolute values, we don't need them technically, because n is equal to 1, meaning the series will never be negative. It will always be greater than or equal to 1. But nevertheless, the test still comes with absolute value. This is really for you to understand that even though this is not a negative series, we can still use ratio tests. It's really not going to make any difference, but we still use the rule because there was an absolute value, and the absolute value of this is this. So technically, we're still using the absolute value, so we're going to follow the same rules. So now I notice this is a rational fraction, so I can divide every term in the fraction by the term with the highest power in the denominator, and that was n to the first power. So when we plug in n, which is infinity, this goes to 1, by the way, we know that one whole divided into infinitely small pieces gets infinitely smaller, so small, cancels out to be 0. So we're left with 0, 1 plus 0, which is just 0 over 1, which is just 0, which is less than 1. And so rho is less than 1, meaning that our series over here converges absolutely. So let's write our conclusion. Since usually you would take the first thing that you wrote, but because this is already simplified, I'm just going to write it again, is equal to 0, which is less than 1. The ratio test implies that the given series converges absolutely, but they didn't ask us if it converged absolutely. They asked us if it converged or diverged. So we use our number 2 tool in our toolbox, the absolute convergence theorem, that says that if a series converges absolutely, then that same series will also converge. So this is our series, and if we know that it converges absolutely, then we can say that that same series converges. So we say, and absolute convergence implies convergence by the absolute convergence theorem. So the original series, the given series, converges as well. And this is your final answer, your actual answer. This series converges. This pink part is always our extra step when we're dealing with absolute value, because when we have absolute value, remember that means we're no longer dealing with the given series, we're given with the corresponding positive series. Sometimes they're the same, but sometimes they're different. In this case, both of these are the same because this is already a positive series. So even if you put absolute value, it's still the same. But regardless, if you use absolute value, you have to use this rule, even though in this case it's the same. And remember that our number 1 tool in our toolbox was a definition that says that if a series with absolute value, so the corresponding positive series, converges, then we can say that the given series converges absolutely. That's what this ratio test tells us. So they take care of that part for us. Our only part in ratio and root test is to use our number 2 tool in our toolbox, which is the absolute convergence theorem, and go from this part, from here, which is what a ratio test tells us, and say if any series converges absolutely, then we know that that same series converges as well. That is what the absolute convergence test tells us. So we're taking this part and we're saying if we know that the series converges absolutely, which we know, we can use the absolute convergence theorem to say that the same series converges as well. And so using these 2 tools together, they form kind of a chain to get to our final answer, which is that this series converges.